Hi, I'm REDOX. You've seen me in such fine quality epic chemistry educational videos, such as AP Chemistry is not for the weak-hearted, and AP Biology and AP Environmental Science. They are tough AP courses in their own right. Okay, this is the lecture that I wish I could have given you guys, but I ran out of time. And this is really aimed specifically for the people who are looking at AP Bio, AP Environmental Science, and AP Chemistry. Looking at Chapter 17a, redox reactions. So the first thing about it is, redox is short for oxidation reduction. That's what's going on. And exactly what in the world's happening? Well, you're getting electrons being moved from one atom to another. Okay, so that means inevitably an atom could lose maybe one or more electrons, okay, and another atom could lose one, could pick up, gain one or more electrons, okay? You can't have one without the other. They always have to occur together, okay? So how do we remember those? Well, there's a couple in here. One is Leo the Lion says grr. Loss of electrons is oxidation. Gain of electrons is reduction. This is a classic. That's how I first learned it. Okay, there is oil rig, where oxidation is loss or oxidation is losing. Reduction is gaining. Thus the term oil rig. So those are two easy ways to remember redox. If an atom loses electrons, it's an oxidation. If atoms pick up electrons, it's reduction. So with that, here's an example of a loss of electrons. Here's Mg, and results in Mg2 plus with the loss of 2 electrons. So what happens? Our oxidation number becomes more positive because we lost 2 electrons. That's an oxidation process. It's a loss of electrons. Okay? Now, what do we mean? Is there a difference between oxidation, loss of electrons, and oxidation number? Remember with the idea, it's two separate things here. If we look at the oxidation number, we're looking at the positive or negative charges an atom or a polyatomic ion would have. Okay? Because if you have an atom or a molecule that has a total charge of 0, there is really no oxidation number. It's 0 and it's nice and balanced. But in this case here, oxidation number becomes more positive because we lose the electrons. And when we look at the oxidation number, we're looking at the charge here. Okay? But the process of losing electrons, that is oxidation. So there's two things that are going on. Reduction is the opposite. Okay, we can talk about the gain of electrons. Here's our Mg2 plus 2 electrons, and we get Mg as a solid. So the idea behind reduction, it reduces the oxidation number. Okay, now remember, both oxidation and reduction happen at the same time. So when we talk about agents, like oxidizing and reducing agents, what are we really talking about? Well, think of an agent as something that makes something happen. Think about it that way, okay? So if a reducing agent is a substance that reduces another substance, in other words, it causes something else to be reduced. It has atoms that donate electrons, so a reducing agent is oxidized in redox reactions. Whereas the reducing agent gives up electrons, okay, the oxidizing agent picks up electrons. Okay, so that's the idea behind it, between oxidizing and reducing agent. So oxidizing agent examples like oxygen, ozone, hydrogen peroxide, cleaners, and bleach. Reducing agent examples would include things like carbon, carbon monoxide, and vitamin C. So if we look at a reducing agent here, it's got 2 electrons. It goes through, this is compound A, compound B, okay? They meet in our process, okay, of a chemical reaction, and then of course compound A loses the 2 electrons. It is oxidized.
In other words, a reducing agent causes something to pick up electrons. The oxidizing agent causes something to lose electrons. So the oxidizing agent picks up electrons, it's reduced. The reducing agent it ends up giving electrons away, and thus it is oxidized. That's the difference between the two. So electrochemical reactions or electrochemistry, or how in the world do batteries work? Okay, well, here's the thing. Redox reactions can in fact produce electricity, and electricity can produce a redox reaction. Can go both ways. So we have something called electrochemical cells. Now, electrolytes are any substance dissolved in water that conducts electricity. Well, an example of electrolyte, we could look at sodium chloride. That's a good conductor of electricity. You have positive and negative ions in there, okay? So you have anions and cations that are formed in the process. Anions are negative ions, cations are positive ions. Yep, absolutely. So strong electrolyte examples, most of the salts out there, strong acids, strong bases. Now, why would a strong acid and a strong base be a great, strong electrolyte example? Remember the idea about strong and weak. Strong, when we talk about strong acid or strong base, it's how well does it dissolve in water. In fact, it's 100% dissolved in water, which means maximum effectiveness. When we look at weak electrolytes, we can look at weak acids, weak bases, so think like vinegar, acetic acid, okay, and less soluble salts. And then, of course, there are those things that are non-electrolytes. They don't really allow electricity to flow through that well, okay? So, parts of an electrochemical cell, for those people who are wondering, I am done with the basic idea of oxidation or reduction. But if you're interested in basically how batteries work, this is a great opportunity. So if we look at the parts of a battery, okay, and remember the batteries that we have in our cell phones and our, our electric devices, things like that, it operates on the same idea. There's going to be electrodes, there's going to be some kind of a solution, and then there's going to be a kind of salt bridge that's there. Well, there's two kinds of electrochemical cells out there. One's electrolytic, the other is voltaic. The idea about that is looking at spontaneous chemical reactions versus non-spontaneous. So in an electrolytic cell, you've got to put electricity into it in order to make the cell work the right way. Whereas a voltaic cell, that's the battery that we all take advantage of in our cell phones and in our battery powered devices. That's a voltaic cell. It is producing a current. Now, it does get used up, obviously. Whereas electrolytic, it's the opposite. You have to put electricity in to make things run with that. So when we look at the difference, we can look at so here, we're going to go ahead, and I'm just going to go real fast here. Galvanic cell is another term for voltaic. Electrolytic cell, that's the one where you have to put the electricity into it. Now, I'm not going to get into super detail. Here's an iron anode and a copper cathode. Okay, the anode and the cathode, this is the two main parts of the battery system, okay, which we have on all batteries. There is an anode and a cathode. In this case here, we have solutions. Now in the batteries that we're so used to, it's more of a paste. There is a bit of a connection there, what they call a salt bridge, which allows some exchange of ions, because otherwise this won't work quite the right way. Okay, and I'm just doing a really fast thing here. So we can look at the voltage value of cells. If we take iron and we break it up compared to copper here, and we add the electrons to the copper to make it a solid copper. We get that from our copper solution. I'm just giving a very fast explanation, and here we have plus 0.78 volts. Okay, now these are values they've already come up with. Now, that's for the regular volt battery that we're used to. On the other side of the coin, if I wanted to go and add iron back, okay, from the copper, I have to run it backwards. I've got to run the electrical current backwards such that, ladies and gentlemen, the electrons will flow through. Electrons get deposited here, and that attracts the iron ions coming in, and they start to clump on this cathode. So that's why we have our E cell of negative 0.78 volts. We'll get into that a little bit more in AP Chem. Electrolysis is forcing a non-spontaneous redox reaction to occur with the aid of an electrical current in an electrochemical cell. In a way, think about a rechargeable battery. In a rechargeable battery, we put the battery in our phone, we use our phone, battery runs out. It's not going to do anything. Until we recharge it, we put it back in, we plug it in, okay, to whatever electrical outlet we have. And what do? We force a non-spontaneous redox reaction to occur with the aid of an electrical current in the electrochemical cell. So we force the reaction to go the other way. We're feeding electricity into the system. Because when we used it as a regular battery, well, where did that electricity go? It went to power our phones. Think about that, okay? Using electrolytic cells, we talk about cathodes, attracting cations. It's negative, it's reduction, okay? Anode is attracts ions, it's positive, it's oxidation. I love the terms red cat and anox. That is absolutely fantastic for that. So red cat and anox is a way to remember what is happening at the anode and the cathode. At the anode, you have oxidation. At the, okay, anox. Red is reduction, cat is at the cathode. So that's why you have red cat and anox, and that's a nice way to remember about that. Examples of electrolysis where we are running electricity to make the system work: electroplating, silver plating, zinc plating. Okay, if we do aluminum manufacturing, it does require a lot of electrical current to make things happen. Voltaic cells, we already talked a little bit about it. So our batteries that we're familiar with, really it's a collection of voltaic cells. Negative electrodes, positive electrodes. Electrodes may be a liquid or a moist paste, depending on it. Okay, and this is actually the first one done by Volta, and here is one that Volta created using copper, zinc, okay, and a little bit of salt, like salt water soaked, paper soaked in salt water, and he was able to generate electricity out of it. Now, understand something, when you have, and they called it a pila or a pile, okay, today we call it a battery, but the idea is that when you run the electricity, one or the other runs out. That's why a battery will stop working, because it runs out of one thing. If you have a rechargeable battery, then you are able to go and reverse the process by adding electricity, causing the chemical reaction to go backwards. But what about those batteries that are quote-unquote disposable? That's a one-way trip. There is no recharge opportunity for that. That's just a one-way trip with that, okay? Just going very fast here. So we have our salt bridge that allows an exchange of ions to keep things flowing, okay? So we have oxidation here, losing electrons. When the electrons go on here and they flow into the cathode here, well, what's going on is that the zinc is going to start leaving. It's leaving because the electrons aren't there to hold the zinc onto the zinc bar. So what's going to happen is that that bar is going to disintegrate, it will fall apart. Whereas the copper, on the other hand, you have electrons that are piling onto it. So now what you're getting is now copper ions that are in the copper solution, they're now attracted to it. So then the copper starts to pile on the copper cathode. Yeah. Okay. Sign conventions are a common source of confusion. The electrode that emits the electron is always negative. Oxidation always occurs at the anode. Okay? Zinc-Carbon dry cells, alkaline batteries. This is what we're familiar with, type of dry cell battery. Okay, it's a zinc-carbon deal. Common in most consumer products. Lead-acid storage batteries, like rechargeable batteries. reversing the polarity recharges the battery. Okay, and that's it, guys. So we talked about oxidation reduction at the beginning of the chapter, which for AP Bio and APES people, you got off the train. But if you decide to stick around for a little bit of electrochemical action, I exposed you a little bit to something that I intend to cover in more detail in AP Chem the next time around. Okay, that's it, guys. I hope this has been a benefit to you guys. Take care, goodbye, God bless you, and Jesus does love you.